Yeah, go ahead.
Understand. So, for the sake of recording, let me add another welcome to Avi. Nice to have you here.
Thank you.
Let me talk a little bit about this center and what the ideas are. There's some questions that Avi asked initially, saying, is a building in the plan? Is it more students, more visitors, more researchers? So the single answer to that is all of it. That's the aspiration that we have. So all the participants, welcome to Chennai Mathematical Institute, a renowned research and teaching institution in mathematical sciences located in Chennai, India. Many of you would have interacted with its founder and a well-known mathematician, late Dr. C.S. Seshadri, FRS. A center of excellence has been established within CMI to promote advanced research in mathematics, computer science, and physics in collaboration with leading researchers and institutions around the world. This center, named F.C. Kohli Center of Excellence, has been created in honor of the late Dr. F.C. Kohli, a technology veteran in India. Many of the researchers, some of whom will be speaking in the next few days, many of the researchers like Dr. Kumar Murthy, Dr. Rajesh Gopakar, Dr. David Mumford, who have contributed to building CMI, have been equally excited about the new F.C. Kohli Center. The number of passionate researchers and postdocs in mathematical sciences is increasing tremendously in India. Very large numbers. The interest level is very high at this point in time. And there is a need to establish a high-end research facility in this part of the world to enable collaborative work with other similar institutions the world over. Advances in scientific knowledge will progress even more rapidly with the capacity, the capability, and the collaborative culture that this center is expected to create. A little bit about F.C. Kohli. F.C. Kohli is the father of the Indian software and information technology industry. A technocrat with education from Queen's University, Canada, MIT, Boston, and other institutions. This he did in the late 1940s and early 50s. Kohli brought computing to the Tata Group in India in its power stations and distribution in the 50s, in the 1950s. He created Tata Consultancy Services more than 50 years ago, and TCS has remained as the largest tech company in India all these years, with a market value of over US dollars 190 billion, billion with a B, and an employee strength of over 500,000. A very, very large organization, which he pioneered. He was very passionate. He was very passionate and committed to education and research. And until his last breath, he was doing some work in the area of education. He was committed to education and research throughout his life, and in his honor, CMI has established the F.C. Kohli Center of Excellence. CMI welcomes you to the inaugural session and looks forward to working with you to promote the creation of new knowledge in mathematical sciences. The promise of this inaugural set of talks is to open the minds of participants to the areas of pursuit in various parts of the world and to facilitate collaborative effort between like-minded experts for curious and also adventurous interactions. Welcome to all the speakers. Welcome all the participants. Now, over to you, Madhavan.
Thank you so much, Lakshmi. So, as Lakshmi said, this is a new journey for CMI. This center, we hope, will expand and extend our existing commitment to research and teaching in many directions. On the academic side, we hope to have a lot of new activities involving a lot of visitors, PhD students from other institutions. So not only with a view to bootstrapping new areas of research in CMI, but also to benefit the Indian research community at large. So we also hope to work with other centers in India to kind of collaborate and share resources and bring some new activities to the front. We also would like to engage with industry and try to promote some more meaningful collaborations on the research front between Indian industry and Indian academia, which have not really been to the extent that does justice to the fact that the IT industry in India is such a worldwide leader, and there is so much mathematics and mathematical talent and computing talent in India. The two have not really worked together to come up with too much, I would say, meaningful yet on the kind of forefront of research, and we hope that that will change. So, of course, many of the activities that we have planned have to be kind of deferred, partly because of the current COVID situation and not being able to interact in person. So we thought that without waiting forever, we should start with something where we can, as Lakshmi pointed out, bring out some of the excitement that we have about the center. And what we have done is we have engaged a group of speakers who are leaders in their field to come and talk to us about what they are doing and also what needs to be done. So it's a question, not just a question of reporting on research, but also hopefully expanding on what are the interesting open areas across a wide variety of disciplines. So everybody, I hope, will have something to gain from this. So like Lakshmi, I would like to really thank all the speakers who have readily agreed at relatively short notice. And I think everybody has Zoom fatigue, but everybody has gladly agreed to give one more set of talks online for this audience. And we have tried to position it at a time when maximum number of people can attend without too much inconvenience. So that's why it's mostly in this evening, 7:30 p.m. Indian time. So with that, in particular, I would like to invite and welcome our first speaker who's leading off this series of talks, Avi Wigderson. So to most people here, Avi needs no introduction, but it is my honor and obligation to produce one for him. So Avi has won pretty much every award that you can imagine in academia, most recently the Abel Prize. He has also won the Nevanlinna Prize. And in computing, he has won the Knuth Prize, and he has also won the Gödel Prize. So I think it is fair to say that he straddles the worlds of mathematics and computer science with unquestioned authority. And of course, the areas that he has worked on, he has kind of opened new fields and inspired a lot of people who have both worked with him and worked on areas that he has developed. So today he's going to talk to us about imitation games. And so without any further delay, I will hand over to Avi. And thank you, Avi, for patiently listening to this beginning of this series. Over to you, Avi.
Okay, let me share my screen.
Yeah, it's all good.
All good? Okay,
Yes.
just a second. Okay, so first, thank you for the introduction. And I'm, of course, very happy to be here and very happy for you in this inauguration of the Kohli Center at CMI. By the way, you may notice from my voice, I have a cold. Maybe an advantage of the Zoom meetings is that I cannot transmit it yet to anybody else, but I hope my voice will remain for the next hour. Okay, so I want to tell you about imitation games, and I'll explain everything about it. The plan is simple. I want to first talk about the original imitation game, which many of you must have heard of, Turing's model for understanding intelligence. I'll explain the main idea and some generalizations, speculations that one might pursue given this amazing paper. But then I'll switch to the main part of the talk, which are the modern imitation games developed within the theory of computation, which are much more formal and rigorous and open new fields. And I'll talk about only 4 of them. So the same paradigm was used essentially in the heart of any one of them. Cryptography, randomness, aspects of combinatorics and number theory, and then privacy. These are huge fields each, and I'll talk about 10 minutes about each one of them only. There's an advantage if you lose me on one, there'll be another one coming. Yeah, I want to stress that definitions underlying these fields came from, inspired by this imitation game, and they had many major consequences. And then we'll conclude. Okay, so let me start. And first, because this idea is due to Turing, let me give you a quick resume of this amazing, thinker, among the greatest in the 20th century. What he did in a very short life. Many of you know of the first two, just the very science of computing and the very reality of computation really emerged from his 1936 paper as a graduate student. In the early 40s, he was a key player in breaking the Enigma machine of the Nazis, probably shortening the World War II and saving millions of lives. He was interested in really everything. And few know, for example, that one of the most quoted papers in biology is a paper of Turing on morphogenesis. But I'm going to talk about his work in artificial intelligence. So he wrote this paper in 1950, Computing Machinery and Intelligence. For people who never read Turing, I recommend that you read basically all his papers. He writes so eloquently and so clearly and motivates his ideas so well. So this is no exception. He starts his paper by saying, how do I study the question, can machines think? So of course he built computers, he defined algorithms, and he was naturally interested in this question and asked, well, how do you study this? And he says, one thing I can do is just define these notions, a machine, and to think. This is a philosophical or ontological approach. And he says, but then you'll start arguing with me about the definitions themselves. So I'll take another route, and I'll just suggest how to test if machines can think. So this is a very different approach, sort of operational or behavioral. And this is how he suggests doing it. It's a so-called Turing test, a famous Turing test, not the Imitation Game. Suppose somebody, designs a robot or a software that, claims they are intelligent. How do we test it? Well, he suggests that we imagine two worlds, the left and the right, and a person, like a referee or a judge, interacts with each of them just digitally, without, of course, being able to see who's on the other side. And at the end of the day, just decides, maybe says, in this case, we'll say human, maybe in this case, we'll say human too. And intuitively, definition should say that this robot is intelligent if the referee makes a similar guess in both worlds. Maybe in this case, the referee, correctly identified the robot. This robot or software failed the test. But of course, we want to subject this robot not just to one referee. We suggest to test it with many of them. Even so, first of all, the same person, same referee can interact many times and can maybe not say yes or no, human or robot, but maybe just have a confidence level or a statistical bias towards what they believe is. So they may output a number between 0 and 1 about what they think, whether it's a human or not. So if these numbers are close, then we say that it's good. The robot maybe is intelligent or can converse like a human. As I said, you may expose it to other referees. The other referees may have different opinions, but still, if every referee produces a number that is close to the other one in both worlds, the left and the right numbers, these P0 and P1 are close to each other, then we'd say that the robot passed the test because essentially the two words left and right are indistinguishable. So I want to look at this picture. This is a paradigm that will repeat again and again in the talk. This is the idea. You want to test something, some property, you test it by imagining two words and some family of tests, interrogating them, and then you look at what they produce, and if they all, say essentially the same thing, then these things are the same. And how approximately close these two numbers should be, this, of course, a detail that I will not talk about here, which is, of course, important in many cases. So you can, extend this idea to other, notions besides intelligence, and people have done that. You can ask whether a computer can feel empathy, fear, pain, or can be conscious or self-aware. A lot of people write about this. You can ask this about me or about my dog. I mean, in general, it's not clear, what you would do to test this, but what any test you can imagine really checks whether this computer behaves as if it feels. We never know what a person or a machine think. In fact, it's not clear how to distinguish carbon-based machines from silicon-based machines. At any rate, these are all, maybe valuable, and the summary is that there are two ways to go about it, as Turing said. One is objective and ontological, like define them, define these properties. But these definitions may not be testable, may not be falsifiable, they may not have a universal meaning. And we are going to follow Turing in choosing a subjective behavioral definition that is precise and operational and testable and useful. And you'll see in the cases I'll describe, it's actually revolutionary. So I want to talk now about these rigorous imitation games. The paradigm, as before, will be that two things are the same if they cannot be told apart by any reasonable test that's relevant to the issue. These definitions will be formal, mathematical, unlike Turing. And this is primary. Once you have the right definitions, then theories and theorems and proofs and constructions, they all follow once you have the right ones. And we'll see the power of this imitation game paradigm and how it enables, great things in math, science, technology, policy. So let's start. The first topic is cryptography. Cryptography for maybe over 2,000 years focused on encryption, on just hiding secrets. For example, if a general wanted to send a command to the troops, which would be either attack or retreat, without the enemy knowing, they would encrypt it using some function, this ENC function, encrypt function. And here you see the encryption. The purpose, of course, is that they will be indistinguishable from each other, so the enemy will not be, we don't know what they plan. There are many encryption functions, since I say 2000, because the first cipher is attributed to Caesar, the famous letter substitution cipher, which I indeed used in the example above. The Enigma machine is another substitution cipher, which is far more complex and time dependent and key dependent and so on. But basically, you can think of any function and ask, well, is it secure? Can the enemy break it or not? And in fact, the more basic question is, what is secure? And here comes the first imitation game from this seminal paper of Goldwasser and Micali. Here is how they define secure encryption. You want to send one or two messages, look at their encryption, you want them to be indistinguishable. More formally, you want that any efficient algorithm that is looking at these encryptions, and trying to distinguish them, will, you look at what it outputs in the same vein as before. And you say that encryption is secure if no matter which two messages you are looking at, And no matter what efficient algorithm is probing these sequences, what they output is essentially the same number, same fraction. You see, it's an extremely strong definition. It's, I would say, shooting for the moon, because every possible attack is going to fail. There are many things to say about this definition. I'll say a few. First of all, it's the first formal definition of what a secret means. It also shows that any such secure encryption function must be probabilistic, because if the only two messages are, attack or retreat, 0 or 1, and the encryption function was deterministic, the enemy can try applying encryption to each and see what are the results. So that's a fundamental observation. And they show that not only is it a formal definition, but one can achieve such an amazing security based on a clear formal mathematical assumption, namely in that case that factoring is a difficult problem. To know, you can base it on other, such as mathematical assumptions. And this was the beginning of cryptography. Once this was done about 4 decades ago, everything opened up, and cryptography became not just about encryption, but about almost everything we do digitally. Online shopping, contract signing, secret exchange, zero knowledge proofs, internet elections, poker on the telephone, blockchains, digital currency, and all of these can be carried out without any physical implement. This is so much a part of our life that I don't have to elaborate. It all started in this paper, The Mathematical Theory of Cryptography, and then its implementations. I want to stress first theory and then implementation. The definition I showed you for encryption security is just the beginning. When you want to define any of the other objects, you're really facing a cryptographic protocol, not just encryption or applying a function to a message. So I want to give you an example how, again, the imitation game can be used to define, say, the security of a protocol with many participants and many interactions. So again, what is secure? So let me demonstrate this from these papers on secure elections. The idea is that these two worlds you are comparing here are on the left, well, let's call it the ideal world, in which there is a trusted party, which I call here a government. We know how it works. That's how it works still today. Everybody sends their vote to the government, and the government returns the tally, how many, who won, and how many votes for each. In the digital world, when some countries or some, anyway, there are places where there are internet elections, and there are many suggestions for internet protocols for elections. What do you want from a protocol? In what way will it be secure? Well, you think like Turing and say, I want that it will look the same as the ideal world. So, for example, any player, if an algorithm looks at the interaction it has on the left and on the right, it cannot distinguish them. And that's for every player. So even some bad players that are part of the, they cannot cheat, for example, they cannot vote twice. More generally, you want no subset of players to learn more than what they learn from their own votes, and so on. But anyway, a formal definition is suggested here. You say that protocol is secure if it just is indistinguishable from a protocol in the ideal world. And again, this is really underlying, this idea underlies many of the definitions and leads to basically secure protocol designed for any problem under the same assumptions. And of course, we see lots of the physical impacts of this. Okay, so this was about cryptography. I want to switch to the next topic, which is randomness. And again, a fundamental notion. And what is the view of complexity theory on randomness? We know that randomness is amazing. Having it is amazing. First of all, nature seems to supply us with randomness. It is, we believe it in some sense. So let me denote perfect randomness by this, gold coins. It's just like a distribution on bits that is unbiased and independent. And what can we do if we have a source like this? Well, then we have many, many applications, sampling, experiments, probabilistic algorithms, crypto, game theory, gambling, you name it. They predate, science, some of them. But I'll focus on probabilistic algorithms because they capture many of the others and because that's what we know most about. And probabilistic algorithms, at least with our experience in the past 30 years or 40 years, for many problems, they seem to be much faster, exponentially faster than deterministic ones for the same problem, at least as far as we know. So is this power real? Is randomness really having it is exponentially more powerful than not having it? So we'll explore this, and in particular, it's important to explore because we may assume that we have perfect randomness, but you think, is this used in probabilistic algorithms which are being run? So let's imagine three possible worlds. One is the most benevolent. The universe has perfect randomness. We can tap to it, and everything's good. The last one is where the world is deterministic. There's absolutely no randomness, and we just our imagination. A sort of intermediate world, which is really, I think, what we feel, is that there are lots of events in the world, in nature, that seem to supply some weak, randomness, some entropy. They are somewhat unpredictable. Maybe sunspots, stock market fluctuations, weather, radioactive decay, and so on, quantum phenomena. And I want to, denote them by this, antique coins. So in the first world, as I said, then we can, have all these applications. And the question is, if we are in one of the other two worlds that are more realistic somehow, what can we do? So this is what I want to explore. And a key to understanding, in fact, both answers in both worlds is to understand what is a distribution that has some entropy, but maybe the bits are biased or dependent and so on. When is it like random? Well, this begs an imitation game. You can by now do things without me, I assume. You set up these two worlds, and you want to say that the right-hand side is pseudo-random distribution, if whenever you subject it to any efficient algorithm, in particular the algorithm that's going to use these random bits, it's going to behave the same as it did with perfect coins. So even though this distribution may be far from uniform, has low entropy, all you want is that it will fool every efficient algorithm. Once you have this definition, again, it's extremely powerful. It allows composition, amplification. I will not get much into this hardness versus randomness paradigm that I'll explain soon. And practice, these things are actually used in the construction of pseudorandom generators and in cryptography. But the conclusion, once you have this definition and the theorems that follow, is sort of amazing. So we said in the first world we can do everything. In the first world we can do everything. Suppose we have only weak randomness, some sources that produce bits. If we sample the weather, probably the weather tomorrow is like today. So there's some bias and some correlation. What can we do with sources like this? Feeding them directly to algorithms is clearly a bad idea. Nevertheless, it turns out that you can use them for all probabilistic algorithms. So everything that works in the top world will work in this world. And this is a consequence of a theory developed over about a quarter of a century, extractor theory. Extractor is a randomness extraction. It's all about purifying randomness, taking a weak source of randomness and massaging it into looking perfect, extracting the entropy from it. That's one. And this is in the world where we have weak randomness. What if we have no randomness? Well, here we need an assumption. Without an assumption, there is nothing we can do. But the assumption is something everybody believes, that this is that P is different than NP, which in simple layman terms means that some problems that we want to solve are difficult to solve. Maybe the traveling salesman, or maybe solving polynomial equations over finite fields, or you name it. Some problems seem to be difficult. Any problem like this can be used. And once you use it, you get the following. Again, without any randomness, you can still emulate any probabilistic algorithm. This is the hardness versus randomness paradigm. So we assume that we have some hard function and use it to build an appropriate pseudorandom generator. And the upshot is that so in contrast to what we seem to believe, every fast probabilistic algorithm has a deterministic counterpart. So it seems that randomness is much weaker for the purpose of probabilistic algorithms than we observe, but that's a fact. So all you have to believe is P different than NP. Well, I put it in quotes, essentially hardness of some natural function. So this is a sort of major understanding about randomness. And besides, the obvious consequences turned out to have many other unexpected benefits, like leading to constructions of important objects like error correcting codes and expander graphs and many other pseudo-random constructions used, come or fall out from these theories. Okay, so again, imitation game was key in defining what pseudo-randomness is and leading to these big theories. Okay, let me switch gears to talk about a different type of randomness, sort of structural pseudo-randomness, which appears in math and number theory. I'm sorry, and if this was an auditorium, I would ask if there are questions after every section, and I think maybe here it's better to wait to the end. So this happens in computer science as well, and discrete math number theory, and I want to highlight it using this example. So here's Ramsey's theorem, which many of you know. Intuitively, it says that every large enough system must have some nice structure. Doesn't matter how chaotic the system is, there's a part of it that looks very homogeneous. A particular instance is this one. So first I want to define what a periodic sequence is. Periodic sequence, maybe mathematicians prefer arithmetic progressions. It just, here I listed all the integers. I mean, I didn't list all of them. I listed only the first 40, but you can imagine it's continuing. So the bars on the bottom and the top depict some periodic sequences like 7, 11, 15, 19, right? A jump of 4 or a jump of 7. Of course, the integers possess arbitrarily long arithmetic progressions. But suppose I give you just some subset, maybe a dense subset, many integers, maybe 1/10 of all integers, and I ask, can you find long periodic sequences in this dense set? Well, of course, these two examples fall out, they are not there. Which subsets contain long periodic sequences? So long, I mean length 1,000, length 1,000,000, billion. What subsets of the integers have this property? And an amazing theorem of Similarity says that all dense subsets do. So again, if you give me 1/10 of all the integers of your choosing, or 1,000th, or 1 in a million, take every year, it will still, you cannot avoid long arithmetic progressions, arbitrarily long. What if you look at a sparser set, like the primes? Primes, are less than a fixed proportion of all integers. Another famous theorem of Green and Tau says that primes also have this property. how do you, they have arbitrarily long arithmetic progressions. How do you prove something like this? Well, and really fundamental observation of Similarity is to start with the following, which is easy. If the subset is random, if you take one, integer of every 10 or something, 1/10 of the integers at random or 100, then it's easy to prove that it has arbitrarily long arithmetic progressions. Okay, good. So we are done with the random. What do we do about the other, what other subsets do? Like dense sets don't have to be random. The primes are certainly not random. So which subsets look random? And Similarity has a sort of an amazing answer in the same paper. It says, forget about subsets. We'll get to subsets later. Let me talk about which networks look random. And I want to talk about this. And from this, he infers what he needs about subsets too. So now we are to another question, which is, which networks look like random networks? And in what sense? So here is, to explain this, let me define these notions, networks, clusters, and bonds in networks. So here's a network, it can be your roads or internet connections or friends in Facebook, whatever you like. A cluster or community is just any subset. And if you have two subsets, you can talk about the bond between them, which is the fraction of connections between pairs out of all possible connections, okay? Like how dense is the connections between these two subsets. You can do it for any pair of clusters, for any pair of subsets. Okay, so that's a definition of what a bond is. And now, Similarity defines bond similarity of networks. So two networks, N0 and N1, again, we have an imitation game. We want to say that they are alike. They are alike in the bond sense if no matter which two communities you choose, let's say this one, and you look at the bond, you look at the same communities on the right, you see about the same number, okay? And this is true for any subset. There are exponentially many such choices. You don't mind, you want that all of them will satisfy this property, then you call networks bond similar. Okay, so that's an important definition following an imitation game. And now comes the second fundamental result, is what's called the regularity lemma. And he wants to show that every network looks like a random network in this sense. So here's an arbitrary network. And the regularity says that every network is bond similar to a random network. To explain what a random network is, I'll show you in a second. It's just a random network specified by a tiny model. And it turns out that bonds between just very few communities in N0 in any network determine all bonds. It's sort of hard to believe, but let me at least explain in what, how it is done. You just appropriately, cleverly pick a few communities. You just partition the nodes in the network to few communities, in this case 3, red, green, and blue, okay? And you just count the bond between every pair, the reds with the reds, the reds with the blues, the reds with the greens, and so on. And you have this little table, just 3 by 3 table, or maybe it will be 10 by 10. And now you can use this table to generate a random network. You just put these same colored vertices, and you just draw at random edges between them, connections between them, according to this number. Between the red and red, with probability 0.8, there is a connection, red and blue 0.1, and so on. You proceed to create this random network from this template. What Similarity theorem says is that these random networks that you just build from a tiny amount of information is bond similar to the original network. Namely, it resembles it in every pair of subsets, even though you used only a few. This has amazing consequences, but I want to say that it goes way beyond Similarity's dream. We saw that dense graphs, and I didn't tell you dense sequences as well, look random in that sense. This extends to other objects, functions and tables and whatever, matrices and so on. And moreover, bond similarity is not the only test you apply. There are many other tests that are relevant that you should apply. And this same type of theorem, the template theorem, works where the tests are what defines the imitation game of similarity. This follows lots of works in math and in computer science, which I won't talk about, but it led to this really fundamental understanding of structure versus randomness, the dichotomy. And by now it is being used in proofs of mathematical theorems in many other areas that I listed before. And I'm sure, it's a fundamental understanding that when you want to prove that something holds for all objects, you first prove it for random objects, and then you show that the other objects look like random in an appropriate sense. Okay, so this was another major area that I'm now going to close and turn to the last topic I want to talk about, which is privacy. Okay, so we start afresh. What do we want, or what do we mean when we want privacy? Privacy is easy to obtain, but it's hard to obtain if you want utility of the data you want to make private. Specifically, suppose we have a database, many individual records, which contain some data about these individuals. It can be census data or medical data. Once you have data, of course, you have data analysts, the right people or entities who are interested in the data and want to, access it. And this is all for, well, not all, but usually for good purpose. This is a utility part. For example, if it's census data, maybe it will tell you about welfare gaps or about planning or roads or, what have you. If it's medical data, of course, it can be used for drug development and treatment analysis and all the good things that the medical establishment does. So of course there's lots of good things you can do with data once you analyze it. But on the other hand, if an individual is somewhere in the database, like this Jane Doe, she may, be worried of the analysts interrogating the database because it may reveal private things about her. So she can ask, why should I participate in this database? Or should I tell the truth if I'm asked something? So what's a good answer? Of course, this is a fundamental problem. It's well known for decades. And people tried many things. You try to restrict the type of queries that analysts can ask. You could try to filter the answer, like apply some noise to the answer so it will distort somehow the identity of individuals. So you don't answer the query completely, but you add noise to it. Many suggestions like this existed, but they were not formal, mathematical, until this seminal paper of Dwork et al., which again used the imitation game as a template for the definition. So here's their definition of differential privacy. What you want to convince Jane Doe or any individual that it doesn't matter if they participate or not. You say, here are two databases, one containing the record for Jane Doe and one containing one which does not, but is identical otherwise. And you want to guarantee that no matter how it is queried, what you get is about the same number, right? Then Jane Doe should be satisfied. So you want to say that such a filter is differentially private. That's the fundamental definition. If for every adjacent databases, D0 and D1, so adjacent means that they differ only in one record, and every legal query, these two numbers are the same. That's the definition. And again, once you have it, this allows for lots of nice things to happen. You can compose filters. You can quantitatively argue about what happens if you ask many queries. How does this privacy deteriorate? You can try to amplify the accuracy and so on. And it also resists, this kind of definition resists the use of future knowledge, like Jane Doe later will put some information in her website. This cannot affect her privacy under this definition. Maybe even more impressively, many entities have chosen to work with this definition. Maybe the most impressive is that the US government decided to release data from the 2020 census using differentially private mechanisms. And similarly, big companies like Google, Facebook, Amazon claim they release data according to differentially private mechanism. So it's a great success. It's a much younger theory and it's still developing, but it has achieved a lot and it's quite deep by now. But I want to tell you as a last slide about one consequence of it. So you see, in many of these cases, you shoot for something. You develop a theory for purpose, your privacy, and consequences, come out that have nothing to do with privacy. And here's a major one: how this definition impacts science. Okay, so let me explain this. This came up in these two recent papers about 5 years ago. The impact to adaptive data analysis. So what is a situation in science, machine learning, and so on? There's data about something, and scientists probe it, basically iterating process like they ask some queries, they get some answers, they tune the parameters, they maybe change their model or form an hypothesis, and generate new queries. And this, in fact, how labs work, and that seems to be a mode of operation that led us to great things, right? Many discoveries were obtained this way. So what's wrong in this picture? There have been many papers written about what's wrong in this picture, and some use the word crisis, which may be appropriate, like this paper that's very much cited, why most published research findings are wrong. If this is true, we should worry, right? I mean, most research findings are wrong, we should worry. Why should research findings be wrong if this is what's going on? So let's understand this. What's wrong in this picture? Well, data is expensive, so we keep the data and reuse it. And this leads by these adaptive iterations to overfitting. So the models seem to explain the data better and better, but as they do, they become weaker in generalizing the data, because after all, we are not out there to understand the data. What we are out there is to understand some natural phenomena from which we sample the data. And it's only because, getting data is often expensive that we have so many samples. So how can we work with this? I mean, this is a reality that data is expensive. How can we work with this and make the results of the experiments more accurate? Well, here's a suggestion. Even though we care nothing now about privacy at all, let's nevertheless reveal the answers to the scientists or to the machine learning programs through a differentially private mechanism. So we noisify it in the way that they prescribe. It's a theorem, or several theorems, that if we use such a differentially private filter, This prevents overfitting, ensures statistical validity and generalization, despite the fact that data is being reused and that queries are adaptively chosen after answers. Like before, there is a trade-off between the number of queries and the type of queries and so on, but it allows, it's a mathematically rigorous result, allowing scientists to validate their, to actually access the data. They themselves can supply the noise. If they do it, they are honest, and the results will be better. So it's a completely, unexpected use of differential privacy in a question that, was not part of it to begin with. Okay, that was the last topic, so let me conclude. I guess, very good on time. The paradigm of imitation games says that things are identical unless you can tell them apart. This holds for all the examples you've seen, but for lots you didn't see. It's true about diamonds, about Picassos, about news, whether they are real or fake depends only on the tests that you can apply to them. And if you cannot tell them apart, then you might as well call them identical. U is very important here, the collection of tests that is applied. You saw in all my examples, it was very different sets of tests applied to the two worlds we were comparing. So it's subjective. And such behavioral subjective definitions, like imitation games, can be extremely powerful, as we saw in these 4 topics. They may be useful also in this philosophical understanding other notions that are more ephemeral, maybe, as I discussed in the beginning. Going one level higher, I want to say that my field of theory of computation is of course a mathematical science, but it is a large part of it is about modeling. It's a modeling science. Definitions are critical. And in modeling whatever natural phenomena, computational phenomena, it's extremely important to be tuned to the underlying process and the resources it is using. So we saw this in these examples, but maybe I didn't stress it. And again, definitions of central notions are primary. Once you have the right definition, as I said, theories follows with theorems and constructions and so on. And as we saw in these examples, and there are many more, they enable great advances in math, science, technology, and society. Let me conclude with advertisement to a book I wrote that came out 2 years ago that tells much more about the theory of computation and about computational complexity. It is free on my website, online. If you like the cover, you can also buy it, but that's not too important. Okay, let me conclude here. Thank you very, very much.
Thank you, Avi. That was wonderful. So we have some time. If somebody would like to ask a question, you can either post it or let me see.
There are some questions already on the chat, I think.
Yeah, but I think those were early and they were answered. I don't think so.
Okay.
Unless somebody still has a question which is unanswered, but otherwise, please feel free to ask on the chat, or you could even unmute yourself and ask directly.
So one question I have, Avi, so the U that, as you mentioned, is very important. And the U in a Turing machine, was that also, is there a restriction on the computational power of the referee there? Because in the other things...
In Turing's work on artificial intelligence.
Yes.
Yeah, so there, U, he says, is a person. So the tester is a human. That's his suggestion. Of course, you can suggest anything. For him, I think it was natural because many people then and now, doubt or fear or worry about this possibility, or don't believe that it's possible for machines to think or feel or so on. And he suggested we test it, but I think it's good that you suggested in this case to the community that doubts it. And he says, well, let's see. And I think it's a good test if you design such a robot or software that's supposedly intelligent. And of course, we know that many have been, even in the 60s, ELIZA, famous ELIZA, but today many more with the advent of deep learning and so on. You can, and in fact, it's being done. You can test, you can expose it to such tests. People run every year competitions doing imitation games in the sense of Turing. You submit the software and then, you let people try to distinguish it from human and so on. And some, you get prizes and so on. And there are tons of papers written on it. Much as I like, it's absolutely fundamental, I really wanted to stress that that definition is sort of informal because, maybe that was your question, the model of computation or the set of tests is not formally defined. Even if you say human, it's not clear what it means. But we've learned that you can make rigorous definitions, and in the various examples restrict mathematically the set of tests. This gives you a formal definition, and then it can do wonders. I want, by the way, since you mentioned Turing, even in his 1936 paper, where he just defines formally the notion of an algorithm using his Turing machine, he does it sort of implicitly by an imitation game. He says, let us see what we do when we do arithmetic on a piece of paper. And he elaborates this. And he says, so he models an algorithm after the way we calculate. Oh, and he says, well, we have maybe a piece of paper, maybe a grid paper where we write them digits down and we add, an addition problem. And, he wants something that will look like this and will be as simple as possible. And he distills it to this wonderful Turing machine. So even there is some, in his mind, some imitation game, building it, modeling it after human computation.
Correct. Nice.
So, Avi, there's a question about random networks.
Yeah.
So it says, when you say every large network is like a random network, does it mean with respect to some finite set of properties or arbitrary finite set of properties, and with large probability? I mean, what exactly is the scope of this word like?
Yeah, the scope is well defined. It's in terms of bond similarity. So the random network and the networks that originated it are the same, have the same bond for every pair of clusters, for every pair of communities. Even though the random network, was generated by 10 or 100 parameters, and the original network may have had billions of nodes, okay? So it didn't matter. From this property, bond similarity, many other properties follow. This is absolutely crucial for example, for Similarity's theorem. There are counting lemmas, there are, removal lemmas. The people in combinatorics or arithmetic combinatorics know a lot about them. So bond similarity, for mathematicians, this is a cut norm for matrices. Strong notion of cut norm. This is it's a strong pseudorandomness condition, and once you have it, you have many other properties following from it. But somehow it's it's the right one with the right set of tests to choose. So you can think of a pair of clusters as a test to the network, right? What is the bond here and what's the bond there? But many other properties, but the definition just says they are the same. And of course with high probability. I didn't say it, but this will happen with high probability, arbitrarily high, yeah.
So Avi, I had a question about your last comment about differential privacy and the fact that the censors and all these companies are using these filters. So first of all, how difficult is it to actually create such a filter? And secondly, how do you convince somebody that it is actually differentially private?
Yeah, the second question is very hard to answer because it's very, I don't know if this is being discussed. Of course, if somebody is holding the database, you have to trust them to apply the appropriate whatever filter. I mean, even forget differential privacy, you have to trust them that they will ensure whatever privacy they promise. So there's nothing to answer there. The first question, how to apply a differential. So this is in fact very easy. There are several known differentially private mechanisms. Essentially, they add noise to answer. So for example, the query might be, give me the average salary of all people in the database between the ages 30 and 50, who live in New Delhi. And there is an answer to it. So there's a two average, and the filter will simply add a small noise to the answer. Okay. What exactly is the nature of this small noise and how small? These are, important technical details. But there are Laplace mechanisms and Gaussian mechanisms, and they are very easy to apply. So that's it's really no problem. In fact, some of them were suggested even earlier without having the definition. Without it said, okay, you want to ensure some privacy, make it just give an answer that's close to the true answer, but it's not the right one. So anyway, here you can quantify exactly what is the privacy leak for every such filter.
Okay, thanks. Any other questions?
There is one more question, I think. When using the imitation games.
Oh yeah.
I can't. So maybe you should just ask the person to ask the question.
Yeah. Soham, would you like to ask your question directly to explain exactly what you're asking?
Yeah, okay. If that's all right.
Yeah.
Yeah.
So I was wondering, sorry, when using the imitation game to check between the random and non-random objects like bit sequences or networks, so we are generating the random cases as well, right? How do we implicitly know that these are what random situations would look like? Like, isn't there an assumption there implicitly, or is it something like an infinite descent?
No, there's no infinite descent there. It's a definition. It tells you that a distribution looks like another distribution, or the two distributions look the same.
Yeah, no, that's fine. I'm wondering.
Let me just. It's a definition. For every pair of distribution, this either holds or doesn't hold. Okay, or for every network on the left and random network on the right, it either holds or doesn't hold. So the definition has no infinite descent in it. You are absolutely right that it's an additional important question to ask how, let's say a pseudo-random distribution is generated in order to get the consequences I discussed about the power of probabilistic algorithms in a world which, let's say, has no randomness. It's another additional important question which I didn't go into at all. But there's no infinite descent. One is, the definition just tells you when two things are alike and when they are not. That's all. If you want to actually start using the definition and develop a theory and have consequences like I discussed, there's much more work to do, which I didn't even talk about because I wanted to highlight just this paradigm.
Well, thank you.
And for that, you would need your lower bound. You would.
Okay. So looks like, at least from what I can see, the questions have died out. So thank you again, Avi, for a wonderful talk. And thank you all of you who have joined today. And I suppose you have seen the schedule, so you know that there is a variety of talks on a variety of topics coming up. So we hope to see you as many of them as possible. So good night and see you tomorrow.
Thank you. Bye.
Thanks, Avi. Thanks. Bye. Lovely talk, as always. Great talk.